Good morning, guys. My name is Yahya, and today I'll discuss something which I think is important. It's about something called interrupts. So in the beginning, I will discuss the interrupt concept. What is interrupt in general? And I will give you examples of interrupts and real life examples. Then I will give you different types of interrupts. Then I will talk more specifically about a specific type of interrupt, which is called external interrupt of PIC16F887. Then I will utilize the external interrupt in a simple application. So let's get started. Now, before I get into the interrupt, I will just give you a simple example about simply counting upward and counting downward and stuff like that. So we'll write a program that will count up to 10 using 4 LEDs at port C connected to port C as binary counter. Once we reach 10, we should start decrementing back to 0. And we will use go to statement for counting process. I know we can use a for loop, but for the sake of simplicity I will use a go to statement. Then I will repeat the above operation for infinity, which means once I count from 0 up to 10, then once I reach 10 I will go down to 0, then I will start counting upward again and downward again and so on, and back and forth. So this is the circuit diagram. We have the PIC16F887 and we have 4 different LEDs connected to the pins C0, C1 and C2, C3 via 4 resistors. So first let's build up this circuit. I will build it up using this Proteus. I'll pick from libraries, then I will type in PIC16F887. And once I write that properly, I should get one result, which is the one I'm looking after. Then let's give it a second here. Okay. Okay. Now I will double click that, and as you can see, it's in my workspace. Then I need a resistor. Then I need a red LED, which is a red LED. I'm gonna pick the third one from the bottom. And that's it. That's all the components that we need, at least for the time being. Then I'm going to place my components, and I'm going to place a resistor and an LED. Then I'm going to change this resistance value because 10k is too much. Then I'm going to change it to 200 ohms, which is I think efficient enough, which is a good enough value. Then I'm going to block copy this several times. Alright, now I have 4 different LEDs, 4 resistors, and let's block copy this as well to have 4 LEDs. Now, once you're done with this, if you would like to remove these ugly text, you double click, you erase and delete, then double click, erase and delete, double click, backspace and delete. And that's the last thing. And yeah. Alright. Then let's do the connection of others as well. And now let's grab a ground, place endless terminals, then a ground. Then let's do the connection as simple as that. Let's ground these 4 LEDs. Of course you can make your own 4 grounds, but I think 1 ground is more than enough, more than sufficient. Then that's it. That's the circuit diagram. So far that's what we need. I'm gonna save that right away in desktop, and let's call it for my YouTube channel. Then I'm gonna call it interrupt design. Of course, for so far it's not related to interrupt, but this is what I'm going to build on it, an interrupt design. So now we're done with this with the circuit diagram. Let's go to the coding. Now I have here the micro C Pro for PIC, and I'm going to simply click File, New Project, or from this new project icon. Next, then I'm going to browse and locate the folder I just created, which is basically called for my YouTube channel, in order to have my design and my code in the same exact folder. Later on, this will simplify things and to find out the code and the compiled code later on. Then let's call it YouTube, my YouTube channel code, and I will make sure that this is the PIC16F887, and for the time being I'm going to keep this 8 megahertz because I'm not going to connect the hardware, so it doesn't matter. Then that's it. I'm going to close old C files to only keep the one that I'm going to work with. Now, based on my circuit diagram, I have 4 LEDs connected to the microcontroller, so I have to make sure that these pins are configured as an output. So to do that, we use the TRES resistor or tri-state resistor. So TRES C equals to 0. Now we have 3 ways to do it. You can say equals to 0, you can say equal to 0x00 or 0b, and you could type in 8 zeros. For the sake of simplicity, I'm going to call it 0x00, which putting zeros everywhere, which means it's going to configure all the pins as output. Then as a good practice, I would like to make sure that all these LEDs are initially off. How do I do that? By saying port C equal to 0x00. Now, to start the counting process, where was I? Yeah, so the question was asking me to count up to 10. So basically I'm going to use the goto statement. So first of all, I need to create a label. I'm going to call it increment, a colon. Then what I would do is, sorry about that, in order to do this kind of counting, I know I could add up to the port itself, but as a good practice, it's better to declare a variable, right? So that's what I'm going to do here. I'm going to create a variable int, then I'm going to call it counter, then I'm going to initialize it to 0. And by doing that, I do not need to say port C equals to 0x00. I'm going to just call it port C equals to counter. As simple as that. And you could even do it, you can say like that, counter, and you could simply initialize it right here. Even you could initialize it even there, right? Now, in the increment, what I would do is this, counter plus plus, then I'm gonna pass the new value to port C, so counter, then I'm gonna put a delay of 900 milliseconds, which is almost a second, for us to be able to view and see that the counter has actually been incremented. Then I will just do a simple an if statement. So if my counter is less than 10, so we would like to count to 10. So if the counter is less than 10, we would like to simply increment again. We would like to increment again. How do you do that? By using the goto statement. So we go to the increment label, and this will keep on and on. So the first time, of course it's going to be 0, and of course I need to put a delay so that we are able to view the port C having a value of 0. Then the second step is the second step I count up, so I increment by 1, so the counter will be having 1 replacing the 0. So I'll pass 1 to port C and I will wait. Then 1 of course is less than 10, so it's gonna go to increment. Then 1 plus 1 is 2. Then I'm gonna pass 2 to the port C. Then delay. Then 3, 4, 5, 6, 7. Then 8. 8 is less than 10. Go into increment. So I'm gonna 8 plus 1 is 9. I'm gonna pass the 9. Then wait. Then 9 is less than 10, which is good. Then it's going to increment. Then we are going to see 9 plus 1, which is 10. Then I'm going to pass the 10 to port C. Then I'm going to delay it for us to view that. Then I'm going to check, is 10 less than 10, which is obviously not. So I'm done with this. It's not going to be repeated again, right? So the next step is, so far this code will increment from pretty much 0 up to 10. So the next step is to decrement now from 10 back to 0. So decrement I'm gonna create a label called a decrement, and alright, then I would say counter minus minus, then I would say port C equals to counter. I'm gonna pass the new value of the counter, which in this case will be 10 minus 1, which is a 9. Then I'm gonna put a delay so that we are able to view this value. Then I'm going to put some sort of a comparison here via the if condition. Then I'm gonna say counter. Now what I want to keep decrementing until I reach 0. So as long as counter is greater than 0, I should keep on decrementing. I should keep decrementing, right? So if it's 5, if it's 4, if it's 2, I still need to decrement. How do I decrement? By simply going to this decrement label, and that's it. Now the question is telling you that repeat the above operation for infinity. This means I need to include or enclose all of this written code within a loop which loops infinity indefinitely. So I need to enclose all of these lines into a loop which loops indefinitely. How do I do that? I'm going to cut that. I'm going to type in a while loop, and I'm going to call it a while one. So while true, which means it's always going to loop. It's never going to stop, right? Then I'm going to paste right there my code, and bam, that's it. This code right there will basically increment from 0, initially 0, up to 10. Then this code will decrement down to 0. Okay, sorry about that. So this will decrement down to 0 because it's going to display 9, then 8, then 10, and then 9, then 8, then 7, then 6, then 5, then 4, and then 3, then 2. 2 is greater than 0. Go. Then 2 minus 1 is 1. Display the 1. Then 1 is greater than 0. Yes, it's going to jump. Then 1 minus 1, 0. Pass to C. Then what we are going to do is C. The 0 is not greater than 0, so it's not going to go to the decrement. So it's going to skip this condition. So once it skips it, it will go right there. And what this will do is it will, since we are doing it in a while loop, it's going to increment again, and the 0 will be incremented to 1, and so on. That's it. That's how I do the incrementation part, how we count up from 0 to 10, then from decrement from 10 down to 0, and how do I repeat the whole process again and again via a while loop. Now let's simulate this. So I will double click on that. Before I go to this, I make sure that I compile my code and I don't get any errors right here. Then I go to simulation, I double click this, then I go to processor clock frequency. Since I specified it to be 8 megahertz, I will simply choose 8 megahertz. Then I'll click that folder. Since I put my design and my code in the same exact folder, I will be able to locate it right in front of me, which is the hex file, which is the compiled code. And that's it. Once I run this, I should be able to see it counting 1, 2, 3, 4, 5, 6, then 7, then 8, then 9, then 10. Then it should decrement 9, 8, 7, 6, 4, 3, 2, and 1, and 0, then 1 again, and so on. So you get the idea now, right? Now the next step that we would like to do is as follows. I would need to introduce the interrupt concept. So what is interrupt? Now, so interrupt is basically something that happens. In order to explain that is when I'm explaining a lecture, when I'm explaining a lab, then my phone rings. What happens is that I have 3 options: either to silent the phone or close it right away. So this will basically an interrupt for 2 seconds, 1 or 2 seconds, right? The other option is to pick up the phone and to tell the caller that sorry, I have a lecture, call me back later. So this will basically interrupt for like few seconds, maybe 10 seconds, 15 seconds, and so on. And the third option is for me to pick up the phone, and then I could simply start talking to the caller and ignore the whole lecture, which is rude. I wouldn't do that. So this means we have different types of interrupt for different periods, and it has different impacts. So that's the interrupt in general. So why interrupt is important? Because let's assume that you're working in a nuclear plant and timing is important. So now, previously, what I've taught that we can use for loops, while loops, etc. So when something is happening, then the program is stuck somewhere. So the program is basically looping somewhere, and it cannot leave the loop unless you shut down the whole microcontroller, which is terrible. So assuming that there's something something emergency happened, and maybe the nuclear plant temperature has gone up, so you should take immediate action. You should not wait until these for loops are basically finished. You should take immediate action, and you should interrupt the whole process. And how do we do that? Using interrupt. Now there are different types of interrupt. There is something called software interrupts, and there is another thing which is called hardware interrupts. Software interrupts, such as the ones associated with overflow registers. So when basically so far we know that the PIC16F887 is an 8-bit size register. So this means it can take up to 2 raised to the power of 8, which is 255 if you counted the 0. So if you exceeded this number, we will have an overflow, and we have an internal interrupt which basically reacts to this overflow part. So now we have the software interrupt, such as the internal interrupt, and we have hardware interrupt, such as the interrupt on change, which are associated with keyboards. We also have the interrupt, which is basically called the external interrupt. That's what we are going to discuss today. So external interrupt, basically it's basically a physical thing. So if an emergency thing is like an emergency button, think of it like a red emergency button that you press so that you interrupt the whole thing and execute a more important function. So in our case, we would like to cool down the solar plant, right? So for the next step is to basically to locate where is that internal interrupt is located. Oh my god, this sounded so bad. Alright, so we need to know where that external interrupt is located. So first of all, if you look carefully here, this RB0. This RB0 has 3 options: RB0, AN12, and INT. So the first one is straightforward. RB0, which means this pin, we could use it as a digital input, as a digital output. It's simple. And this AN12, this means that this pen could be also used as an analog input, right? So it can also accept some data from sensors and so on, right? And this pen could be also used as an INT, which is the interrupt. So that's exactly where it is. That's exactly where it's located. Now, in this example, we'll write the program. We'll count up to 10. That's what we did so far. That's the previous example. Then once we reach 10, it will start decrementing. So the first 3 lines, we've done that in example 1. Now, what am I interested in? I'm interested in is using external interrupt at B0. That's exactly where it is. Using external interrupt at B0, interrupt the counting process. So we have to interrupt it and blink a yellow LED connected to D7 7 times. So basically, this is basically what we have done so far. We have 4 LEDs as a counter to count from 0 to 10, from 10 to 0, blah blah blah. We're done with this. Then now we would like, once we press this button which is connected to B0, we would like to stop or interrupt this counting process, and we would like to blink this yellow LED 7 times, I think. Yes, 7 times. Now the good thing about the interrupt is that if I'm counting, let's say 1, 2, then 3, then 4, then 5, then 6, now then 7. So then I press the button. Of course it will stay at 7, and it will blink this 7 times. Now once the blinking process is done, the counting process should continue. I should see 7, then 8. I should not see 0 again. So again, if for example, if I'm counting 1, 2, and 3, then I press the button. Of course, the last count is 3, and this will blink, which is basically 7 times, since this is the interrupt part. Then once the blinking process is done, I should not start counting from 0 again. I should continue where I left. And the only possible way that, at least as far as I know, the only possible way that I know is to use the interrupt, because the interrupt, it will leave this process and it will execute a more important process. In our case, this yellow LED blinking, this represents the cooling process of the nuclear plant, right? Which is really important, you know. After you cool it down, you continue whatever the main process of the nuclear plant, measuring the sensors, the whole algorithm, etc. Now, to do this thing, first of all, let's add these two to the design. Now, this is a simple yellow LED, and this is basically a button configured in the active high configuration, and there is a reason for that, but let's do it, then I'll explain why in the upcoming slides. So let's add these LEDs. So basically I don't have a yellow LED right here, so let's get it. So I need a yellow LED, and of course I have a resistor, so I need a push button, and that's an SPST, single pole single throw pin push button. That's it. I will start by placing the button, the resistor, then think another resistor, and a yellow LED. And of course this value is too big for an LED, it will never turn on, so let's change that to, for example, 200 ohms. And where did I connect this? To the 7. It could be connected anywhere, it doesn't matter. Then let's flip this and let's rotate it anti-clockwise. Let's connect that down there. And now let's just, now this is important, you should never snap it like this, although it looks connected, but it is not. Anyways, so you have to connect each and everything manually. So I will simply connect that, and of course I need a ground right here, and I need a ground right here. The ground here, I could connect it here, but to be consistent and to make it look nice, I would simply right click, place terminals and a ground. Then I need a ground for this resistor, which is a pull down resistor, and I need a power. This power represents a 5 volt DC, 5 volts DC, and that's it. That's pretty much all I need. So I just need to connect this with the B0. So let me pull it down. So the B0 right there. That's it. Now let me save that and let me go back to my slides. So in order to, first of all, let me explain how to use the external interrupt. So to use the external interrupt, we use different special function registers, because so far I explained, so far we were using the TRES special function register and the port special function register. So TRES will control the pins in or out, so you're going to configure the pins as input or output. Is it going to receive some information or is going to output some information? The port is basically related to status. You are going to output logic 0, turning off the LED, outputting logic 1, turning on the LEDs, and so on. So there are more special function registers. We have the INTCON special function register. INTCON is basically short for interrupt configuration, and it is a really special function register. Each pin means something, and for the time being we'll focus on 3 bits: the GIE, the INTE, and INTF. So let's take them one by one. The first one is GIE. GIE is global interrupt enable. So think of it as this. Think of it as you have like a tree and you have small branches, or think of it that you have a like a big kind of like a water going through, and you have the main pipeline that you want to let the main water stream to flow, or to stop it. So think of it as this. This is the general interrupt enable bit. So it enables all unmasked interrupts. So this enables in general the enables us to use interrupts in general. So this is basically, think of it as a main circuit breaker, right? It's not like a circuit breaker for like one room or two rooms. Think of it as the whole main circuit breaker for the whole house. Think of it as that. Okay, so by placing a 1, it will enable all the interrupts. So that's what we are going to do. We are going to put a 1 in there. So how do we do that? Let me just open up a notepad and simply do it while we're going through this step by step. So the first thing is basically, in order to enable all the pins, enable all the interrupt, enable the global interrupt pin or the bit, I need to write int con. Now, in order to access this bit, there are two ways to do it. One way is to say .f7, since it's located in bit number 7, or to say .GIE, and it works both ways. Then, in order to enable the global interrupt enable bit, you have to place 1 to enable all the unmasked interrupts. So I'm going to put and place a 1 there. That's the first step. The second step is which is the int E. Int E is external interrupt enable bit. So external interrupt enable bit. And if you place a 1, it will enable the external interrupt. If you place a 0, it will disable it. For the time being, we would like to enable it. So how do we do it? Well, by placing a 1. So again, I need to place an int con, which is interrupt configuration, then INTE. Then I'm going to place a 1 there to enable external interrupt. And the first line, to enable interrupts in general. Okay, and last but not least, which is the int F. And this int F, this is interrupt flag, and this is really important. And basically, the interrupt flag is basically occurred. Basically, it's kind of like, think of it as a flag. When an external interrupt occurs, this interrupt bit will have a 1. Whenever there is no interrupt, it will have a 0. So think of it as, that's this one. So think of it as this. If an external interrupt happens, a 0, if an external interrupt happens, this bit will have a 1. If no external interrupt happens, this bit will have a 0. So this will keep a record, because if we compare it and if we say if this bit has a logic 1, do so and so, this means that if this bit has a 1, this means an external interrupt has occurred, right? Now, this line is really important. This external interrupt flag must be cleared in software, because if a previous external interrupt occurs, maybe in the previous program, and you haven't cleared it, it will think that there's an external interrupt. So you must clear it. How do we clear that? Straightforward. We simply need to write again int con, but this time not .GIE, it's going to be in .interrupt flag. Then I'm going to place a 0. So think of it as this. It's like a good practice to make sure that the LEDs are switched off initially, right? So it is similar to that. It's a good practice to make sure that, and to clear out the flags, right? Especially the external interrupt flag. Then this to clear out external interrupt flag. And yeah, that's pretty much about it. So these 3 lines are important to activate the external interrupt. So I'm going to cut that. I'm going to paste it in my code. I'm going to paste it in the initialization part. And that's it. That's pretty much what do I need. Now, that's not the end of it, because so far I didn't write any code regarding this yellow LED flashing or blinking, right? I did not do that. So I need to write this somewhere. Now, if I'm going to write it inside this while loop, then what's the use of doing all of this? It's ridiculous, right? So it must be another way of doing it, and that's actually what I'm going to do now. I'm going to create a function, so void interrupt. Now, watch carefully what will happen here. Void interrupt. You can see that automatically Micro C Pro for PIC recognized this function, because actually the word interrupt, if you pronounce it properly, if you write it properly, it is associated with the actual external interrupt, actual external interrupt. So when you activate the external interrupt, whenever any external interrupt occurs, it will always refer to this function. So whatever you write here is going to be executed. Now, as basically a good practice, it's also important to make sure that not all the time you go to the interrupt, you execute what's inside. You also have to be more intelligent. So how do we do that? We have to check this interrupt flag, right? So here's how I'm going to do it. So F interrupt flag equals 1. So this means that external interrupt occurs or happened. So whenever external interrupt happens, I need to do something about that. In the example I gave you, I need to cool down the nuclear plant. In this simple example, I just need to blink the LED 7 times. So blinking 7 times, I'm going to use a for loop for the sake of simplicity. So using a for loop, I need to use another variable. I'm going to call it I. So I'm going to say for, then I'm going to simply write it right here 7 times. So I equals to 1, then I less than or equal to 7, then I plus plus. Then what I'm going to do now, I need to blink the LED connected to, where did I connect it? To D7. Of course, I did not declare this pin as an output, so I need to declare this pin as an output first. And to do that, I need to do it in the declaration part, or the initialization part, which is right here. So trace, and I connected to D7, so press D, and I'm going to only declare this pin as an output. I'm going to ignore the others. So .F7 equals to 0, so that F7 equals to 0, declaring it as an output. Then I'm going to make sure that it's initially off by writing port D.F7 equals to 0, and that's it. That's how I declare that the D7, only the D7 is output, ignoring the other D pins. I don't care about the other D pins. And this line is placing a 0 in the port D7, which means that it's initially off. Anyways, now I can simply start blinking and everything. So to blink an LED, I need to turn it on, then delay in millisecond. And the question was blinking it for how many times? So 200 milliseconds. So 200 milliseconds. Then I need to, sorry about that. Oops. Then I need to switch it off like that, so equals to 0. Now it is very important that line, the flag must be cleared in software. So yes, we managed to detect that there's an external interrupt, but this also means that I also need to clear it out. So how do I clear it out? I simply say intcon dot interrupt flag is equals to 0. So I will do. You could do it after the if statement, but I would like to do it within the if statement, because otherwise it's redundant, if you get my point. So that's pretty much about it. So what I did is basically I did some declaration, and these 3 lines is to activate the external interrupt feature, and these lines is basically example 1, counting from 0 to 10, then counting down from 10 down to 0, and of course this process will be repeated indefinitely using this while loop. And the void interrupt, I hope I write it properly. Interrupt, yep, interrupt, yes. So I managed to do it. So whenever any external interrupt happens, in our case, if we press that button, right, so this interrupt flag will see a logic 1, right? So whenever an external interrupt occurs, this flag will be set to high. It will be activated. It will have a logic 1. So that's why we are going to execute this this kind of code, which is blinking yellow LED, which is like an alarm, something happens, you know. Then we're going to clear out this interrupt flag. So let's compile this code and go to simulation and try to run this. So as you see now, it's counting upward. Everything is fine. 3, then 4, then 5, 6, 7. Then let's press that. Nothing happens, which is totally weird. Well, the main reason why, because this pin has an AN12 in it, and I forgot to tell you about that, because this pin has the option of accepting analog or digital. So I need to tell it that yes, you are getting an input, and it's also digital, not analog. So how to do that? It's quite simple. I need to go right here and say ansel, and I don't quite remember, but I think this ends an AN12. It's part of ansel H. So equals to 0. This will tell it that from AN8 up to AN13 or 14, I don't remember, these pins which has an AN from AN8 up to AN13 maybe, you should accept a digital input, not an analog input. So let's run it again. So 1, then 2, then 3, press that. Oh, nothing happens. So what's going on with that? If I press it, yes, one goes. So let's figure it out. Maybe the interrupt is written in a wrong way, I think. So maybe that. I don't think that's the reason though. Let's run it again. 2 and 3. Yep. So I think I misspelled it somehow. So 5, 6, 7, and 8. Blinking, then it should continue. 9, then 10. Then it will decrement. 9, 8, 7, 6, 5, then 4, then of course this is 3, so it's gonna blink. Then it should be 2 now. Then 2, then 1, and so on. At any instant I press this interrupt, it will interrupt the whole process, do this blinking, and it will return to the same exact point. That's basically the last part I was going to explain to you. That's what's happening here. We've done initialization, we've done some main code, which this represents that this is the main program of maybe the nuclear plant is working, the algorithm, the main software, I don't care. And whenever any emergency occurs, the power plant temperature has gone up, you need to cool it down. So you need to exit from the main program, then execute a more important more important algorithm to save the whole thing, to save the whole situation. Then once this cooling process is done, you just need to go back to the main program. I need to come back to the same exact position where you left. I do not want to start from the beginning. I want to continue where I left. That's pretty much about it for today's video, guys. Hope you enjoyed it, and sorry for taking so long. See you guys next time.